Okay, we are continuing with the topic of light. This is chapter 29 in the, I think the 9th edition of the book. So, Huygens principle. We're introducing the concept of Huygens principle, which is that every point on a wave, on the wavefront, can be regarded as a new source of wavelets, which then combine to produce the next wavefront and so on. What does this mean? If you look at a candle flame, what happens is point A creates waves that go out that are centered on A. Then point B creates waves that are centered on B, and so on. Right? So these light rays go out. So if you look at the waves that are coming from A here, so this figure is the same as this but turned on its side. What happens is A sends out a wave front, kind of like the ripples. If you think of the ripples here in the water, you can see the ripples are propagating outwards, right? They go outwards. So this could be seen as one of the ripples. Now, Huygens principle states that you can look at the behavior of light as if every single one of the positions on this wavefront is then creating new waves. So here is an example. If you look at each of these points here, this creates a circle that's centered about here, and similarly with each of these. So the resulting wavefront is the summation of all the wavefronts that arise from here. So if you sum them all up, you end up with this wavefront. If you sum up all the waves from here, you end up with this. So that's basically all that Huygens principle is stating. And that we don't use this principle very much in this course, but in higher level physics courses you would use Huygens principle to determine the shape of waves in complex situations and so on. Okay, on to the second slide.
Is it only on waves, or can it be like in air?
This works for any kind of wave, whether the wave is in air or not. Like light, for instance, if you were to take this room and evacuate it so there's no air in the room, light would still be able to propagate through the room, right? Okay, so introducing, sorry?
I said we got a full house in here today.
Yes, the best students are here. Okay, so introducing the concept of diffraction. Now, diffraction we mentioned briefly in a previous class, and we said that diffraction was a phenomenon where light could travel around corners. It looks as if light or waves or energy can travel around a corner. So here, for instance, think of this as like a pool of water or the ocean where you've got the waves that are coming in. Here's a wall that's blocking the motion of the waves. There's a window in the wall. So what happens is the waves that travel here from the open ocean up to the wall, they stop. They're not able to make it past the wall here. They're not able to make it past the wall here. But at this place here where there's a window, the waves are able to make it through. So as they make it through, you can see that these waves with a certain wavelength, they are propagating through. Now what's striking about this is instead of just traveling in a straight line, you can see that the waves are actually curving around. Some of the wave energy is making it all the way up. So you can see this is faint ripples way out here, right? And there are faint ripples way out here, all the way to here. So some of the wave energy is really opening out and traveling. So it looks as if a beam of waves coming like this, instead of just traveling straight, is actually being able to curve around the edge. So this would be kind of like saying if we were to shoot a gun through this door. Let's say you open the door and you shoot a gun multiple times, right? Now typically what we would expect is that the bullets would make it straight through and hit the wall on the other side. It would be very surprising for one of the bullets to go through the door, make a right turn, and make it way all the way out down the corridor to the door at the other end. Right? That would be very unusual with a bullet, but waves are able to do that. The phenomenon by which they turn around the corner and travel is what's called diffraction. Right? So now, if we were to make this window smaller, as I make the window smaller, what happens is the angle to which the waves go outwards actually increases. So notice that with a wide window, what happens is the wave energy is traveling in this region, right? It doesn't seem to get very much past that point. When I make the window smaller, notice the wave energy is traveling all the way out here and here as well. The waves are making it all the way around the corner, right? So this is, as soon as the wave gets out the door, it's able to turn 90 degrees in one direction or the other. So diffraction is that phenomenon where this bending of light, the light passes around an object or through a narrow slit, causing the light to spread out as opposed to being in a very tight beam. So that is a phenomenon that's typically unique to waves rather than to BBs or ping pong balls or whatever. Okay, continuing with diffraction. Now if we had a light source like a bulb here, a window with a wide opening, a shadow cast right from this window, you can see the light coming through the window here. This is pretty sharp. Now if we were to make this window smaller so it becomes a narrow slit, now what happens is the light that's coming through that narrow slit, instead of forming a narrow slit, ends up creating a diffuse pattern. If you look at the cross section of the intensity, if I drew a line here and looked at the intensity along the y-axis, I get this figure where intensity of the light along the y-axis as a function of position along the x-axis, with this being the slit, right? So this is the slit, this is the actual slit width. You can see that some of the light is actually curving around the edges of the slit, traveling through an angle that's wider than the slit. So you end up with a peak, sometimes called a lobe. So this is the main peak, and then it turns out there's a dip, then there's a secondary peak on either side, or a fringe. And as you go further out, there are more fringes, but they're very much lower than this in intensity. So you can kind of see this where you have a razor blade and a monochromatic, that's a single color, single frequency laser light is used to scan the razor blade, and you can see that the laser beam is actually diffracting around the edges. That's why we see these fringes. Can you see the fringes there? Right? So it's like bright, dark bands. Those fringes correspond to these bands that we talked about. So this whole phenomenon is what's called diffraction. Okay, we've looked at interference in a previous lecture as well, briefly. Interference is where you have two different waves, two or more different waves coming together, and when the peaks all add up, you get a greater peak. When the troughs all add up, you get a greater trough. When a peak cancels a trough, they kind of reduce the relative intensity of the two. Oui, mademoiselle?
Is sound, is it
Same thing happens with sound, right? Extra credit to you. This is why if you happen to be at a party or something, if one person is speaking at a certain volume but you're at a party, you know how like this everybody's sound adds up to a first approximation, right? Problem with sound is there's such a variety of different frequencies and so on. If the sound were all of one particular frequency, then you could have very obvious interference like this. So interference is where you're superimposing two different waves. And if let's say that you've got two different waves, they have the same wavelength. From here to here is the same as from here to here, and you line the peaks up. So when you line the peaks up and the troughs up, the peaks reinforce to a greater extent, the trough reinforces to a greater extent. Now, if you line these up so that this peak matches the trough. So from here to here, what we see is constructive interference. They're adding up, right? The two waves are adding up, making a much bigger wave. If you do it like this, where you have a peak here and a trough here, you add them up, they will cancel each other. Now if it turns out you have a wave that is this has a different wavelength than this, what happens is then this peak cancels out this peak, but there's a little residue left over, and then similarly here, and so you'll end up with partial cancellation of the two waves, right? So the intensity is lower as a whole. So here's the illustration. The schematic at the top is exactly what we saw on the previous slide, and here is an application. Okay, the way you create these waves is in a physics lab. You can actually have a square container of water, like a pan of water, and what happens is, so you got the water and it's stationary, so that's smooth surface. Now you could end up with a little, like a probe or something, right? So here's the water and you got the probe, and what happens is you can bring the probe down to touch the water, to bounce the water once, and it'll create one ripple. Then take it up, hit it again, creates a second ripple. So you could keep doing that with a certain frequency, and that would create a series of these ripples heading out. Now instead of having just one probe, you have two probes. Here's a probe and one next to it, and you do that, right? And you can adjust the amplitude, the intensity with which you hit the water. You can also adjust the frequency with which you hit the water. Now let's say that you tune these so that both of these are the same amplitude and the same frequency. What happens is you've got a set of ripples that are going out from this probe, a second set of ripples that are heading out from this probe. Now when you can adjust the distance between these sources, if you will. Now each of those probe heads is a source of waves. You can adjust the distance between the two of these, so it's more evident here that they are closer and here they're further apart. Now notice as you look at the waves that are going out, right? So here's the ripple from the lower probe or the lower source, right? The ripple heading out. This is then interfering with the ripple from this one, right? So you can see this ripple is interfering with this ripple, creating an additional pattern, right? So if you look at this additional pattern, notice that as you go further out, you can see that there is a band here and there's a band here with lower intensity, right? This is a region where those two ripples are undergoing destructive interference. So they're undergoing something like this, where you actually have no oscillation of the water or very little oscillation of the water. At the middle of these, so here's a band of destructive interference. Here's a band of destructive interference, band, destructive interference. Now at the halfway point between the two destructive interference locations, you end up with the maximum interference. So the upward motion of the wave and the lowered, right, the trough of the wave are twice the intensity, right, the height, compared to a single one of these ripples. So this is an illustration in real life of this kind of interference. Now, how many of you have heard of the Bermuda Triangle? Okay, so you know that there are some people who believe that it's true in the sense that we don't know if it's urban legend. A disproportionate number of ships and boats and planes, even allegedly, have disappeared in the Bermuda Triangle compared to rest elsewhere in the ocean, right? So I don't know for a fact. I've never looked at the statistics to say if that is real or if it's just an urban legend, right? It could be an urban legend where like one person claims that and then everybody believes it, right? Just because it's in print, it must be true. So therefore, now let's say for a moment that the statistics are true. Let's say that really there's a larger number of ships and boats and so on that disappear there compared to elsewhere in the oceans in the world. So there are different possible hypotheses, right? One hypothesis is the mothership that could be sucking them up, right? Another possible, and remember that a hypothesis is a guess, right? So, and now, another possible hypothesis is that there are like freak storms that come up, maybe, right? And there are a couple of other hypotheses. Another hypothesis is along the lines of this. That is, if in certain parts of the world you can have storm fronts coming together, like it's two different storms, right, or waves from two different wind systems coming together, and where they come together, you could end up with waves that are abnormally high. So there's a phenomenon called killer waves that people did not believe. They thought that they were just, like sailors were making these claims during the days of wooden ships, right? Obviously they were high on something, and they thought, right? So they claimed these things, nobody believed them, but now what's happened is there's documentation of killer waves out of a completely calm ocean, right? Or a not very, very rough ocean. All of a sudden there's this huge wave that could be like 30, 40, 100 feet tall. Comes out of nowhere, right? And so now we actually have, I think YouTube has some video footage from a cruise ship where one of these waves just came out of the ocean that they like were totally surprised by and came as high. You know how tall the big cruise ships are, right? They can be like 10 stories tall, 5 stories taller than that. It took out all the captain's, the highest deck, right? But there's a captain, right? Basically took out the glass. So it was high enough to come along and basically take out the captain. I mean, it didn't kill the captain, but basically take out the captain's, what do you call that, nest? Or whatever the captain does. So it's not clear what is causing these killer waves, but one possible model for this is some kind of interference among the waves. So if the Bermuda Triangle thing statistically is true, here's one model for what may be happening is waves like this are rising because of some special configuration of the ocean and the land mass and so forth in that area, right? There's another hypothesis that may be even more credible than this hypothesis, and that is the methane gas hypothesis, which is basically that if you look at the bottom of the ocean, in some parts of the ocean, there's a huge amount of biomass, plants of different kinds, right? As well as fish and so on. And what happens is these plants can then generate methane bubbles, small amounts of bubbles. Just like if you have ferns or whatever, something in, not ferns, but greenery inside your fish tank, and if you look at them, sometimes you can see little bubbles on the leaves, right? That's the respiration of the leaves. So what happens is something disturbs one of these areas with lots of plants, you can have a stream of these little bubbles coming up. Now, if one bubble hits another bubble, the two can coalesce and become a bigger bubble. So if that process occurs enough, you can end up with a huge bubble, particularly because if the ocean is deep enough, you end up with very high pressure. So a small bubble, about the size of my fist, in principle, could become bigger and bigger as it comes further up. So then you could end up with one huge bubble that's, 30, 40 feet across. So for or 100 feet across, in principle, right? As it comes up to the ocean. So to a ship that's just doing its own thing, right? Let's say it's calm water, here's a ship just traveling along, or a boat, and all of a sudden one of these huge bubbles shows up under it. As far as the ship is concerned or the boat is concerned, now you fall into a 30 or a 40 foot hole that suddenly appears in the ocean. So you fall into it and the ocean closes, right? So closes over you. And that's the end of that. Okay, so that's another hypothesis. Which of these is true? I don't know. Okay, continuing with the topic of interference. So here is two slits, right? Here's a window, not a window. Here's a sheet of paper or a piece of wood or something with two narrow slits. Here's monochromatic light, the laser, and the laser comes through and hits this. And if you did not have interference, you'd expect to end up with two bright lines, right? However, in the presence of interference, you don't end up with two bright lines. You end up with a whole series of bright lines. Bright, dark, right? If you did a cross section across this, drew a line like this, and look at the intensity along y-axis, you'll end up with a plot that looks like this. Intensity on this axis versus the screen width, and you end up with all these peaks, right, with an envelope function superimposed. So this is bright, dark, bright, dark, bright, dark, bright, dark, just like we see here. This is in the presence of interference, which occurs if you have monochromatic light of exactly the same wavelength, frequency, and so on, coming from a laser, for instance. Now, if you didn't have monochromatic light, you'd expect something like this. You'd expect a general peak like this from the first slit and a peak like this from the second slit. Actually, if you didn't have monochromatic light and you didn't have diffraction, you just end up with two very sharp bands. You wouldn't end up with the spreading, right? If you have diffraction, you'd end up with the spreading. So if you add it up without interference, if you added up this diffracted peak, let's say, and this diffracted peak, you'd expect to end up with one big peak instead of two. But what we see in practice is when you add, isn't it strange, you add these two things up and you end up with a dip. Really weird. The reason why it's a dip is because there is, in some locations, there's constructive interference between this peak and that peak. In some locations, there's destructive interference between the light from here and there. And that's why I end up with these patterns. So that's a experimental confirmation of interference. So you can apply this technologically. This is used in there are various applications where you need to make glass or plastic with very, very flat surfaces. So this is one way of testing let's say that your job is to create some plastic discs like this that are very, very flat on the surface. What happens is this is a test disc that is very flat. You take the test disc and put it on top of the manufactured disc, and then what happens is you look from the top and you see these kind of fringes. This tells you that the thickness, the gap between the top disc and the bottom disc is varying in width, right? It's varying in height along those fringes. What's happening is, if you look at the schematic beneath this, here's the upper glass, there's the lower glass, and there's an air wedge. And what happens is light rays, say the black light ray goes through the top glass, through the air wedge, and reflects off the top surface of the bottom glass. Say here's the black ray. The blue ray comes here, reflects off the bottom surface of the top glass. So blue ray is reflecting here, black ray is reflecting here. So these two rays, they travel a different distance, and since they travel a difference, there's what's called a path length difference. The path of the black ray is longer by this distance plus this distance than the path of the blue ray. This path length difference then translates into a wavelength, a frequency difference, right? Not a frequency, but really a wavelength in terms of the position of the waves difference. And that then creates, as the eye looks from at different positions, it creates constructive or destructive interference, resulting in these kinds of fringes. So you could have constructive interference here, destructive, constructive, creating those interference. Similar phenomenon which is called Newton's rings when it applies to something like a contact lens. Let's say you have a contact lens that is on, say, let's say that you're manufacturing contact lenses and you're trying to make sure that the contact lenses are properly symmetric and so forth. You put the contact lens on top of sheet of glass or something of that sort. Now what happens is light rays come down. They come, one ray bounces, reflects off of this bottom side of the contact lens. The other one travels through the reflecting bottom glass. There's an air wedge in between, and so when you scan this, you end up with constructive and destructive interference, creating these rings, and these rings are called Newton's rings. So constructive, destructive, and so on. So if there's some kind of a defect in your contact lens, it'll show up as a blob somewhere here, right? So what will happen is, instead of perfectly circular rings, you'll end up with oval rings, or the ring with a sudden bump, and so on. So that's one way you could do quality control on contact lenses, just as an example. Continuing with interference, you've probably all seen this, right? Here's a kid who's totally like enthralled by this bubble, right? So you create these bubbles, and if you look at the surface of the bubble, you see this rainbow pattern in the bubble, right? And you notice the rainbow pattern moves, right? Moves around the bubble. What is happening with the soap bubble is similar to what we see. Let's say it hasn't rained in Phoenix for quite a while, and then it rains, and then you see this like little sheen of water on the asphalt. You look at it, and what happens is you see rainbows, right? What's happening is gasoline that has whatever soaked into, if you will, the asphalt comes up, floats above the water. So here's the water. Above this is a thin sheet of gasoline. Now light rays coming from the sun, from the ambient, come down here. This ray, the black ray, comes down to the bottom of the gasoline and reflects off. The blue ray comes and reflects off the top of the gasoline. So again, this black ray has traveled an extra distance, which is proportional to the thickness of the gasoline. This creates a phase shift between these two waves, between the black wave and the blue wave, creating an interference effect when the eye looks down at it. So if you look at it in a certain angle, what happens is certain colors get destructive interference. So what is left? So if you see a certain spot and it looks red, that means like blue and green were destructively interfered out. You look a little away from that and you see blue, which means the red and the green got interfered out. Look a little further away and the other two colors get interfered out, right? And so that's how we see those patterns. Now the same effect is happening on a soap bubble, except that the film of soap is changing. As time goes on, it's evaporating, right? And as it evaporates, and what happens is the soap bubble is not exactly uniform either. So what happens is then the thickness of the bubble changes at different places, causing those interference fringes to move around the bubble until it pops. That's pretty neat. So introducing the concept of polarization. Polarization in the context of light. We have already talked about polarization in the context of electrostatic charges, right? We said polarization is where all the positive charges go to one side and the negative charges go to the other side. Now, that's to do with charges. Now, the same term applied, unfortunately, to light means something slightly different, a bit different, very different. Okay, so polarization with light is talking about the alignment of the transverse electric vibrations of the electromagnetic radiation. Now, we said that a light wave is an electromagnetic wave, and an electromagnetic wave has an electric wave that's oscillating hooked to a magnetic wave that's oscillating perpendicular to it, right? So the electric wave is oscillating in the vertical plane, the horizontal plane has the magnetic field. So the waves are doing this, right? I'm not very good at this, right? So here's the electric wave and here's the magnetic wave, and they're doing it together, right? So considering just the electric component, what happens is, if you created this wave by taking a electron and bouncing it vertically, you end up with a vertical electric wave. That's here. Instead of bouncing the electron vertically, I take the electron and I bounce it from side to side, right? Horizontally. Now what happens is the electron oscillates like this, creating a wave, electric wave that's traveling horizontally. That is, it's oscillating horizontally. So this is a vertically polarized electric wave, which is always hooked up with a horizontally polarized magnetic wave. But when we're thinking of polarization, we're just speaking of the electric wave to make things sound simpler. So this is vertically polarized, and this is a light wave because the frequency is such that it's in the light regime. This is a horizontally polarized light wave. Now I can take the electron and bounce it from here, and then bounce it from here, and bounce it. See what I'm doing, right? So I can change the direction, right, the axis about which I'm bouncing the electron, and that will create a mixed polarized or an unpolarized light wave. Now if I have a whole bunch of different photons of light, and a photon is basically a particle of light, or it's a wave train, it's a little section of the wave, right, of light, and one wave is vertically polarized, another one is horizontally polarized, one is polarized at some angle, and these angles are spread throughout the 360 degrees. We end up with normal unpolarized light, which is what kind of light that we get typically from the sun and from most light sources, right? So illustration of this, here's a woman with whatever, skipping rope. She oscillates the rope up and down and creates a vertically polarized wave, or she oscillates it from side to side, creating a horizontally polarized wave. Now you can have filters, right? You probably, some fraction of you probably have glasses that are polarized, right? How many of you have sunglasses that are polarized? Okay, couple of you, 3 of you, right? So with polarized sunglasses, if you look at the blue sky, what happens? It cuts out, what the polarized glasses do is they cut out the scattered light coming in from the atmosphere. So you will actually find that you can see mountains at the distance more clearly with the polarized glasses, right? And you can also hold up a polarized versus an unpolarized glass, let's say that the same intensity of darkness, and you will find as you look up at the sky that the polarized glasses are darker, right? Yes, sir?
I think I've asked someone this before. Why don't they use polarized glass? Everyone gets blinded on the road at night by headlights. Why don't they use polarized glass in windshields and then make polarized glass that's on a slant for headlights? Is that like a patent buyout thing, or is that just something that everyone's overlooked? Or
did you ever look through your polarized glasses at too?
yeah, and it's all like
So you see a rainbow.
right.
It's kind of weird.
Yeah.
I think it'd probably be the same effect.
Well, yeah, you know, I don't know. It just seems, in theory, it makes sense because you could have your high beams on driving around everywhere, and everyone's only going to see, you know, so
Actually,
much of the light.
Yes, that's a good idea.
But you know, I don't know if it would cause like a rainbow effect and everyone would be tripping out like they're on acid.
Some of it may be cost, but that's a good idea. I mean, it's to just like test it out,
Well,
see if it makes.
It's kind of like a guy who made a carburetor that got 250 miles a gallon or whatever. It's $4. You know, you never hear about that kind of stuff, but I'm sure there's underhanded business going on. Like glass.
I have heard of that urban legend.
Yeah.
I don't believe
it's
it.
all hearsay. You know?
Yes, that particular one about the 250-mile carburetor per gallon carburetor. If you can find any documentation of it, totally extra credit to you. Send it to me. I would love that. My take is that it's an urban legend. That I mean, if anybody had actually invented something like that,
Well,
governments all over the world would be falling over themselves for it.
yeah, well,
right?
it's just the concept of it. You know, they got bought out because it was too good. You know, is this something where a glass company was like, hey, we already have millions of windshields that aren't polarized, and now there's a standard to check out polarized windshields?
I'm skeptical of that. Yeah, I think it's a good idea.
Yeah.
I think it's a good idea, but you'll have to test it out, see if it makes sense.
It's a conspiracy theory, I guess.
There's a cost factor associated with
That would be a key thing.
luxury cars have polarized lenses on their headlights. The ones that say we focus our headlights, basically all they're doing is polarizing them.
Okay.
Oh, so there already are headlights that are polarized? Okay.
I think Mercedes and BMW does.
Cool.
General
Yes.
Lexus does, I think.
Yeah, but definitely it'll be more expensive.
As far as the windshield is concerned, they would have to find a different way to do it because the polarizing lens is not safety glass. You
Okay.
have to have safety glass so that if something hits that windshield,
It won't blow
it
up.
spiders instead of shatters.
Right.
Yeah. What you could do is put a polarizing film over your windshield. Take safety glass, put a polarizing film over, right? So I mean, this is the nature of entrepreneurship, and this is the great thing about a free market capitalism, is people come up with an idea like this, say, hey, if we can make money at it, let's do it, right?
More entrepreneurs should take physics.
Did you say? Oh, entrepreneurs should take physics? Yeah, there are. Good point. Thank you. Extra credit to you. I fully support the notion.
The problem is because if you cross the filters, like that second picture there,
you get
you
nothing.
can't see through it.
Right.
Yeah.
Yeah, so you have to have like a standard, or hope that a car doesn't flip in front of you, or you know that kind of stuff.
Okay.
If you're wearing polarized sunglasses or
Right.
glasses,
You have to have some
all
sort
of a
of
sudden they put the wrong filter on their windshield and all of a sudden you can't drive.
right.
Yeah, so that's a good segue to what this woman has two parallel filters that are allowing only the vertically polarized light through, so you can still see her face, right? A little dimmer than her forehead. Now, if she crosses the filter, so this filter allows only horizontally polarized light, this allows only vertically polarized light, so what happens is no light is able to get through here. So that's why it's totally dark. You can't see her teeth at all. Whereas over here you can see the light that's through one of the filters, and here it's the clearest without any light being cut out. Okay, so polarization, continuing with polarization. So the light that's coming out of a flashlight is